All right, so there are some programming techniques for some of the sensors I would like you guys to know. Okay, so I'm gonna try to go through all these things for today, so we don't have to go through the slides in the future. So next, actually on Friday, we'll do the joystick tutorial, which is in 602 lab. Okay, Vernal 602. So the optical encoder. So this is a device that is able to, it works like a potential meter. So one of the labs are going to use this one. It's very interesting. And I think I should show a red one here for you to look at it. Let's be one of the labs. Okay, so it looks like very similar to a potential meter, but when you rotate it, it's not going to let you rotate it continuously. You will hear the click click, so which is actually making all these the little blockers. These are the two optical sensors. It didn't show a laser here, but there is a tiny, you can just imagine it's IR emitter, and on the other side is a receiver, things like that. And whenever it is on, so when you rotate the plate, there's a knob, right? You can rotate it. And whenever this one is being rotated clockwise, then let's assume that when A is on the top of this part, it's outputting a high signal, a logic high. So that's how you can tell if this encoder is being rotated clockwise or counterclockwise, and how many times it's being rotated. So it's not a potential meter. Okay, you'll hear that little stops. So how to program it? So here's a question. So the input is just a mechanical input. You will just twist that knob, and then it's going to rotate. And the output are output A, output B, and you'll be able to receive that kind of pulse. So definitely you have to power it up. I mean, without this kind of actuator, I mean, how can you sense that rotation? Here's my question. How can you sense that? So for example, the direction of the rotation, right, is the first question. Something is being rotated. So first, the direction of the rotation. Second, the angle of the rotation. And let's just think about it. Like, what's the other way you can sense it? So for example, you want to mount a sensor, optical sensor to the tire of the car, and sense the speed of the car. So you can do that actually, right? So by using that, so you mount that optical sensor at a fixed location, and when the tire rotates, it's gonna block that light signal, so it's not, no signal will be received by the receiver. So it will receive pulses, and you can calculate the time between each pulse to calculate the speed of the tire. But this is very similar, right? So first, it is able to sense the direction of the rotation. Second, it is able to sense how many or what's the angle of the rotation. So totally there are, depends on the different types of encoder. If there are like totally 36 steps for the entire 360 degree for the circle, then there will be like 10 steps, right? But actually the one we have can definitely has more. I think I couldn't remember how many, but there are more. You can feel that when you rotate it. So what's inside are these two, and the signal output from these two light sensors are being connected to the pin of the module. Let me see if I have a picture of it. So I don't. Okay. It's on one of the tutorials. See if I can find it somewhere. So that was for last year I taught this class, and there's a tutorial of using the encoder to build a two-joint robot arm. So these are the encoders. So if you look at it, DT and plus, you see which is being shorted to A and or which is being shorted to B. So I think one of them is A, one of them is B, and you just short these two pins to the. You can use Arduino, you can use any type of microcontroller to sense that. So the output from A and B are going to be something like this. Because B is being placed behind A, so whenever this thing is being rotated, A and B are not rotated, right? So they are still there. They are being mounted to the module. But whenever this wheel spins, if A on the top of this part, let's say it's going to output a high, and B was still low. Whenever that happens, there's a rising edge. Whenever the rising edge happens, B is still here. So let's assume this place, this location, whenever it's not on the top of this block, is outputting a voltage low, right? So whenever A experiences a rising edge, at that moment, B is low. All right, that's how you can program it. To find out the direction of the rotation. So whenever A has a rising edge, like this, B is low. So think about that. How can I write the Arduino code? So first, what's the direction of the rotation? Clockwise, counterclockwise? No. So whenever this wheel spins, A will be on the top of this block first, which will output a high. Yeah, no, yeah, they are mounted to the block. No, they don't. Yeah. So only the wheel spins, but not these two detectors. So detectors usually they are being mounted to a wire, right? If something is mounted to a wire, it cannot rotate it. So the sensors are not being rotated. It's usually being mounted to somewhere. So it's clockwise. Just imagine that this wheel is being rotated like in that direction, right? Like this. So A, when A is on the top of this block, it's going to output high. And whenever, just right at that moment, because you can write a code and it's going to run the loop in the microcontroller really quickly. So the loop is being executed back and forth really quickly in your microcontroller. So that's why whenever this one experiences the rising edge, you can detect, you can just try to find out the input for B at that moment. So whenever A is high, A is going to high, you can think about how you can program it. It's going to be an if statement, right? So whenever this is going high, and if B is low, then I can say it's being rotated clockwise for once, for one step. Okay. Similarly, if you rotate that wheel counterclockwise, like in that direction, so this block is wide enough to have both A and B to be on the top of it, right? So A and B will have the same signal output. And whenever A changes, because it's rotating in that direction, you can imagine that right now, B is here, A is here, is right before getting out of this block. So when A changes at that moment, A and B has the same state. All right, so in that case, it is rotating counterclockwise. So there are two ways to program this. Let's go back here. And I'm going to introduce one, and the other one, I will just let you know the algorithm. Ask you guys to program it in your homework. So let's look at this one. It depends on different design. It can be high, can be low. I don't know. But I think the one we have, whenever A is on the top of the block, it is high. So for here, it's high. When A is on top, it's high. So whenever there's a rising edge for A, B is low. So that's clockwise. It's rotating clockwise. I can see from here as well, right? So when A is changing from low to high, B is low. Does that make sense? So look at this diagram. So when A changes from low to high, B is low, and we can tell it's rotating clockwise because when A is on top, it's just trying to get on the top of this block, so it's receiving a rising edge. So B was low at that moment. That's why it's clockwise. What about this one? Whenever the feature here is when A is changing from low to high, B is high. Let's see if that's true. Whenever this guy is rotating in that direction, right? Let's think about that. B has been on the top of this one. It's already reporting a high, and keep rotating. So it's going to move A on the top of the graph as well, and so it's going to give you a high as well. But A is going to change from low to high. B has been high for a while. So B has been high for a while, and A changes from low to high, and B has to be high at the same time whenever A changes from low to high. Boring? No, it's like tired. Everyone is tired on Wednesday. Wednesday is the worst. Thursday is fine. Friday is the best. It's a different story. The comparing. Makes sense? So we're going to program it right now? Kind of. At least we know the key point to differentiate these two states or the two directions. So let's look at one example. So there are several tactics you need to learn how to program it. First, how do you detect the rising edge? Let's look at one example on the paper first. This is just some very common algorithms you need to know because it's just super common in real world. Sounds like it's pretty simple, right? But how do you detect a rising edge at a digital pin? Well, let's just think about it first before I go on. So, for example, you are writing Arduino code, and there's a digital read from a pin. Of the Arduino, right? For example, this is D1, that's Arduino, and you have a switch, that's VDD, that's a pull-up resistor, and how do you want to do that? Here's a switch. Let me see. It's better to do this actually, a pull down resistor, and then yeah, that's VDD, and here's the output to the microcontroller. That's 10K. So before I close the switch, D1 is reading a what? 0, because here's ground and there's no current, so there's no voltage drop. So 0 volts here, 0 volts here is reading a 0. If I close the switch at that moment, what's going to happen? It's going to vibrate. So what D1 is going to see is it used to be 0, but now when you close the switch, it's a mechanical switch. So you're going to vibrate a little bit before it's stabilized at high. So that's whatever D1 is going to see. So how can I detect that rising edge? It's vibrating. It's going to vibrate. It's called debounce, right? Switch debounce. How do you debounce it? You can debounce it electrically, use a SR latch, or you can do it in the software. So how to do it in the software? This is very common. You want to know that. It's very common that shows up on the interview. There's a question like how to debounce it, how to write the software to debounce it. So you thought it's going to be this, right? But actually it's not. There are several ways to do it. You can detect the change and then delay for doesn't have to be exactly this much, delay for a few milliseconds, and then detect it again, see if it's still high. Right? That's one way to do it. And so let's come back to this one. It's a very similar technique to be used for this one. So the first algorithm, counterclockwise, after A changes its state, A and B are in the same state. Is that true for counterclockwise? It is. Only for the right side. Yeah, whenever facing that direction, whenever A changes the state, B is still on top. So A and B are on top of this guy. That's true. For clockwise, after A changes its state, A and B are in the different states. That's why I'm converting code here. So that's a variable host that output from A to a digital rate before you rotate anything. So if you detect a change, so if A changes its state, can be from high to low, can be from low to high, doesn't matter, because it can be rotated from the control plane, control block to the IT area. Right? Just keep rotating in that direction. So when A changes its state, we detect the difference between the last state and the current state. Because this is a loop, right? So a full array controller can run the loop all the time, back and forth very quickly. Just keep reading the state of A. If there's no change, which means it's not being rotated. We won't execute this if state. What this is going to do is just keep reading A and assign to the last state. It's going to be the same state. It's not being rotated. This part will be executed. This one and this one. You come back and forth. So if that encoder is being rotated, the state of A will be changed. I mean, the speed you are rotating is way slower than the microcontroller can run this code, run this loop. Especially some can do it quickly. Whenever there's a change, it's able to detect that. Whenever I detect a change, and I have to do a judgment here again, which is if B, the current B, is the same as the current A or not, which is exactly in this one, A and B are in the same state. So if they are different, which is actually this, A and B are in the different states. So just add one to the counter. So the counter counts how many steps is being rotated clockwise. Okay. I mean, it's just outputting a number, either positive number or negative number to a serial monitor. So the counter is +1. You can look at the numbers are getting higher and higher, which means it's being rotated clockwise. If you are getting a negative number, you know that it's being rotated counterclockwise. And that carries a lot of information. If you want to use that information directly and send it to any other places, you can try to do a if statement to compare that one with 0. If it's larger than 0, then it's being clockwise. If it's negative, then it's counterclockwise. Okay. So that carries enough information. That's the result here, the encoder. All right, so that's algorithm 1. So the second one is for you guys.
But before we move forward, let's see if this is true, right? Counterclockwise, when A changes from low to high, B is high. Is that true? Huh? So for the first one, think about that. It's rotating in that direction, and B has been here, right? And A moves to here. A from here to here is not changing the state. It only changes the state when that one moves on the top of the block, but B is still here, right? When these two are here, and A will change the state from low to high, and B is still high. That's counterclockwise. And for clockwise, when A changes from low to high, B is low. Right? But when A goes from low to high, B is still low. So how can we program it though? So does this cover, the other case, which is when both A and B are on the top of the block, but they are moving out of the block. So A is going to change from high to low. It doesn't cover that, right? So the result is you rotate it for multiple times, for twice, then it's going to trigger one change. Because it's not counting the other situation, which is both A and B are already on the top of the block, but they are moving out from the block. Which is okay, but it's just you just have to rotate it for more time to get the same count. That's what I'm thinking from the algorithm. So try it and see what's going to happen. So what's the code can be used for that A changes from low to high? So from low to high is a rising edge. I have one example on the microcontroller website. Let's take a look at it. So that's a push button detection. Let me see if this is a good example or not. So the point here is you just want to detect the rising edge, and that one should only respond for once. But the code is keep detecting that voltage high after that.
So it's keep outputting the same result. So I know this is kind of think about that. If there's a rising edge like this one, and I only want to count for one, I want to add one to it if I have a rising edge here. But the thing is, it's gonna vibrate for a few times. So if I say like if this pin, if D1 is high, then I'm gonna do something, right? This is flawed. It's not going to work. Why? This cannot be used to detect the rising edge. Why is that? Why it's not going to work? So see here, because the Arduino is going to run that loop very quickly, so it's going to keep detecting that all the time. Yes, whenever there's a rising edge, it is able to detect that high, right? It's going to do this and do this right here. But the thing is, this guy will keep high for a while. It's going to detect the high here, detect the high here, the high here. It's going to keep counting and adding ones to it. So it's not detecting that rising edge for once. So you cannot directly just use the argument like high to detect the rising edge, because it's going to be high for a while. So how can I solve that problem? So what's the difference between the high here and the high here, 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 here? That's how you can tell the difference. That's why you can only detect that high, but not these highs. So for the loop here, you can assign a last state, right? So if the current state is not equal to the last state, which means there must be a change. There must be a change. It can be a rising edge. So this one will detect the rising edge or falling edge. Doesn't matter because there's a change. And I don't care if there's a vibration or not. If there's a change, and then I have to do another if statement. So whenever I detect a change and the current state has to be high, so I can rule out the falling edge version. So the changes can cover this case or this case, and this if statement will rule out this one because the current state is high, so it has to be this one. So whenever there's a change and the current state is high, I will count it. So you're wondering, I mean, after a while, it is always high. So you're detecting a high. Do you have a problem here as well? So this will do the job. Does that make sense? So that's the software debunks. I mean, yes, you can search for this code online whenever you are working on a project. But the thing is, which makes a difference is you know all these techniques whenever you are being asked to solve a problem, you are able to write it just code it up in probably 2 minutes, since you know the trick there. So why this one works? Because right now, so yes, it is keep detecting high, but the thing is, I'm assigning the last state to the current state. So the state is not changing anymore. So that's why it's not getting into this if statement. So this will not be executed. So it's not being counted after the change, right? Any questions on this? So definitely have to do a digital read. From D1. So, no. So this doesn't require delay. Because since the state here, this variable is being changed all the time, the last state has been assigned. Oh, sorry, wrong. So D1 is being read in this cycle, right? For example, it's the same loop. D1 is being read and assigned to state, okay? And this state becomes the last state after this code is being executed. If the state is not changing, then the last state will be high all the time, and it's not going to execute this if statement. Otherwise, it's going to do it because there's a change. The change can be either a rising edge or falling edge. And only when it's a rising edge, it's going to run both of the two if statements and do the count. Otherwise, it won't do the count. Okay, so it's going to be very similar technique being used in a lot of places. For here as well, so when you are doing the homework for this one, A changes from low to high, so you can use that code to detect that rising edge. Okay. Is that clear? All right. So let's get into the second one. So my question here is, because this is LDR, light dependent resistor. So whenever this is being placed in a bright environment, being well illuminated, then the resistance for this resistor is very low, like a wire, short circuit, depends on the intensity of the light. And here's a transistor. Since we don't have to care about the details about it, how to do it, but the thing is, you need to know that if this pin, this wire here, if you have a relatively higher voltage, it's going to open this switch and open the channel here from top to bottom. If you got a low voltage here, it's going to block the channel. And whenever the channel is being turned on, current is going to flow from the top to here. So you get a current, and the current is going to close the switch for the relay. Will provide a power supply to the whatever the load after it. So you can cursor for what? Oh, it's on my monitor.
So for this one, that's a switch. It's a BJT transistor with a switch. If you give a relatively higher voltage, to turn on the switch, current can flow. If you give a low voltage, it's being turned off, so no current. no current runs through this one, it's a relay, no current, and the switch will be open, so no voltage being supplied to the output. You have a load here, then there's nothing. So this can be used as a line dependent switch. That's how that works. And so now let's think about it, because that one will be pretty much zero resistance whenever you have a flashlight to shines on it. So depends on that property. Can you tell that if this is a light sensor or darkness sensor? So just let me know when it's gonna provide the voltage to the load. Whenever it's bright or dark. Let's think about it. So for example, if I have light for this sensor, it's going to be a wire. Okay. So which means because this is relatively high voltage, high resistance, like 10K is a pull down resistor. So this will be shorted to the power supply. So it's giving a relatively higher voltage. To turn on the switch. But does that make sense? I mean, so whenever there's a light, it's going to turn on the voltage here because whenever this becomes a wire, it's sourcing current from the power supply to turn on the switch and current and close the switch, so get a voltage. So light will turn it on. Okay. I think there must be a different circuit. Okay, so it's not here. That's okay, but you guys can understand this circuit, and you know that you can use this LDR as a light sensor to supply a voltage to the load. Is the light sensor providing the voltage also, or voltage from VCC power supply? Yes. Yep. It's a good point. Because R1, usually they are either pull down resistors or pull up resistors, 10K, right? But compared to the LDR, it's whenever it's in dark, it's still a pretty small resistor. Because when LDR is in dark, then it's like 1 million ohm or something. So 10K seems like a short circuit. That's why whenever it's in dark, this is a huge resistance. If you consider this as a voltage divider, it's going to drop most of the voltage here and nothing being left for this resistor. Which means 10 volts, and you've got pretty much 9.8 volts being dropped here. So I have 0.2 volts here, which is pretty similar to ground. It's grounded. That's why whenever it's in dark, you got a 0.2 volts. It's not able to turn on the switch or this transistor. You swap them. Okay, if you have this huge resistor in dark, okay, this huge resistor at the bottom, but this R1 is 10K on top. In dark, you have most of the voltage being dropped to close this RDR, which is 9.8 volts, for example. So you get 9.8 volts here, which is able to turn on this transistor. So whenever it's in dark, this is on, and it's going to allow current flow through it, and then close the switch and provide a circuit. If you have an LED here, whenever it's in dark, you turn on the LED. When there's a power outage, right? So it's dark and then turn on the LED. That's how the lights work.
That can be one of the applications you can see in real world. The LiDAR, what the cops use to track your speed and pull you up. And you know, they are just lasers. And I have one I bought when I was in graduate school. This one. It's being disassembled from the factory, one of the factories, I don't know where, but they are being sold on eBay. So original cost for each of these ones are like $2,000, but you know you can still buy these ones from eBay for only $200 or so, and they are very sensitive. So the
laser emitter and receiver are both inside the box, and that's somewhere you can adjust the output voltage. I don't know what that one does. So these are the connectors. We can connect these ones to amplifier and then to our oscilloscope. We can see the displacement of any moving part by placing this on top of that object to be detected. So the sensitivity is pretty high.
Arguably like 10 nanometers, but I don't know if that's true, but at least 1 micron, I can tell, micrometer level sensitivity. And the range of detection is usually only tens of millimeters. So if there's an application to for quality control in the industry, in the factory, you want to use this one to detect if there's any bumps, you know, things like that on the product. That's a good thing to use, but definitely not the water level detection for the bridge. The range is only like 10 millimeters. The sensitivity is high. But there are some other LiDAR sensors can be used for a longer range. So this one is called a PMT. So that's a photo multiplier tube. It is able to amplify the photon. So it's used to detect very weak light signal. It's very similar to the photodiode. I showed you like this one. So that's a simple photodiode.
It's being reverse biased. You need a different amplifier to amplify it. This is a low pass filter here. So it's converting the photo current into a voltage because the current is going to flow in that direction from here to here. So the current will be converted into voltage because there's a voltage drop called RF, and there will be a voltage being detected from here. So that's a very typical transimpedance amplifier for the photodiode. So that's one of the photo sensors you can use. It's 1D, right? You cannot get a camera, like a 2D image from this. It's the 1D signal. If you look at that from a computer monitor, it's going to be a spike.
It's very similar to the PMTs. Different technology, but also a 1D detector. So on the left-hand side, that's the internal structure of the PMT. So photon will get into the photo multiplier tube.
Here, that's the input, and it's going to output the voltage or current. You can buy different types of PMTs. It can be a current output or it can be a voltage output. If it's a current output, you still have to design a TIA, a transimpedance amplifier, to convert that current into voltage. But I prefer using a voltage version, so you can look at their data sheet. You can see they already have a TIA embedded into the sensor. So you can directly amplify, use the voltage amplifier to amplify the voltage output over here.
So this is a PMT output amplifier, and this is from a real product. I forgot if this is from the product I worked with a company when I was in use the other one, but it's a very similar circuit.
So current, the PMT has a current output. And this looks like an inverting amplifier, but this is actually whenever you get a current input, this is being used as a TIA, transimpedance amplifier, because current get into here, and here's the gain, being amplified by the gain, which is exactly the value of the resistors. So that's called a transimpedance amplifier. And current input will give you a voltage output here, and then directly use a voltage follower. So it's not amplifying anything, but being used as a buffer to give you a pretty high output resistance. So all the resistors and anything of the load is not going to affect the resistance over there. So it's not being divided also. Because this guy has the highest input impedance and output impedance as well, because you can see here is a gate of the transistor, which means this one has the highest resistance in the following circuit. So it's going to drop most of the voltage over here. So it's not changing the supply voltage to the following. So it's not, whenever you want to supply a voltage to the following circuit, you want to use the voltage buffer like this, voltage follower. The gain is 1. Negative feedback, gain is 1. And that's just a regulator we have used in the past. That's how we can amplify a current signal from PMT or optical signal. Keep in mind, either photodiode or PMT, you need a what to amplify that signal. Because the optical signal is being converted into current signal. So you get that current signal, immediately you will need a transimpedance amplifier. Keep in mind, okay, you need a transimpedance amplifier or TIA, transimpedance amplifier or TIA, which is exactly an inverting amplifier. Okay, so or op-amp with an inverting configuration, and that's a transimpedance amplifier. Pretty simple. And for the 2D optical sensors like the CCDs, and CCDs are able to transfer that charge from one location to another. So if you look at here, so what the CCD does is it's relaying that charge from one location to the output of the sensor. So for example, you have 3 phases, okay? And one is here, so whenever an optical signal hit that sensor, there will be charges accumulated depending on the intensity of the light. So there will be a different amount of charges being accumulated underneath the electrode. And then you activate this one first, and then it's going to be moved to the charge. The charge will be moved to here a little bit because of the electric field, and then just activate each one subsequently. So eventually you can move the charges from the original place. Because the 2D sensor, you want to eventually move all the signal, all the charges to one place, and then do ADC conversion, and then send them out serially to outside. So that's why I have to have 3 phases, different phases to move them, to do the relay. Like move it here, then I turn on this one, so I can attract it to here. Then I turn this one, it's going to be attracted to here. So just do that, so you can move all the charges to the bottom of the 2D array. So here's the difference. CMOS and CCD. So for all the cameras you have in your smartphone, they are all CMOS sensors. The cost is low and it's kind of faster as well.
So CCD is a little bit old, but for the laboratory optical detectors, they still use CCD for a lot of times, probably because of the high resolution or high quality.
You can see how the charges are being moved out. You get a charge and it has to be moved down to here and then to the outside. That's how you can read it out. But you have to do it quickly, so every pixel is not taking a lot of time. They can do it and then get the data together and then send it out for reading. For CMOS, there are tons of literatures online. You can see. So they can either do everyone here is a pixel. It's a pixel. So for your camera, you have millions of pixels. So millions of these little things. But not everyone has a ADC. So usually what they do is they have a row decoder. So they activate this row and send that signal to the bottom. And at the bottom, you have one row of ADC. So you can convert row by row. Okay. So whenever that row is done, you can either save it into the buffer or you have to send it out. So that's why whenever it's displaying all the pixels on the monitor, usually they just place one row of pixel at one time and then scan the monitor. Your eye couldn't resolve it, so it looks like a smooth video. But actually it's not. They're assigning different pixels at one time.
All right. Yeah, I will upload it. So there are some other sensors I have to introduce because this will be on the homework. And I'm asking you guys to program this ultrasonic sensor without using the library. So there are some little things to cover, but not too many left, actually. And I think we'll do it on Friday as well here. Then we're done for the slides, okay? So I'm going to update the website. So Friday, we are still going to meet here. And then we are done for all these slides. So you guys will be ready for the homework assignments. And we'll do the joystick on Monday in 602. So which is actually pretty good, since I will have more time to work on the new lab and to try to give you more space. All right.